We're surrounded by these incredibly complex industrial processes that basically power our entire lives. But keeping them running safely, that is a huge, huge challenge. Today, we're going to pull back the curtain on the invisible network of guardians that stand between a totally normal day and a potential catastrophe. We're talking about industrial safety systems. Let's dive in. Okay, so take a look at this. Seems pretty simple, right? You've got a burner heating up some liquid in a tank and a controller making sure the temperature stays just right. It's a basic heating process you'd find all over the place. But what if I told you that this super simple setup is actually hiding at least 3 different ways to cause a complete disaster? So, what are these dangers we're talking about? Well, first, you've got uncontrolled gas. A leak outside a tank could create a massive explosive cloud, or a flameout inside could just fill the whole tank with unburnt gas. Not good. Second, the liquid itself can be a threat. If it overheats, it can expand, turn into a gas, and build up pressure until the tank literally ruptures. And finally, think about it. Every key component, the sensor, the controller, the valve, is a single point of failure. If any one of them breaks, the whole system is flying blind, which could easily lead to one of those first 2 disasters. So in this explainer, we're basically going to build a fortress of safety around our simple little tank. We'll start by looking at the dangers. Then we'll bring in the core idea of a safety instrumented system. After that, we'll start adding layers for shutdowns and redundancy, guard against specific threats like fire and gas, and finally, we'll look at how you can actually monitor for failures before they even happen. To build our fortress, the foundation has got to be strong, and it's got to be independent. This brings us to our first and honestly most important line of defense, a totally dedicated system that's designed for one job and one job only, and that's safety. This is what's called a safety instrumented system, or an SIS. Now, the really crucial point here is its independence. It uses its own sensors, its own controller, and its own actuators. So why is that so important? Well, think about it. If the main control system is the thing that fails, you absolutely need a completely separate guardian that can step in and force everything into a safe state. Now, not all safety systems are created equal. They're actually rated by something called a safety integrity level, or SIL. Just think of it as a measure of how reliable that system is. A SIL 1 system has the highest chance of failing, while a SIL 4 has the lowest. Most industries are going to be operating in that SIL 2 and SIL 3 range. If a process actually requires SIL 4, it's often a big red flag that the process itself is just too dangerous and probably needs to be completely redesigned from the ground up. So, we have this guardian watching for trouble. But what does it actually do when it finds it? It doesn't just, sound an alarm. It takes control. And it does this through a whole hierarchy of shutdowns and by building in a really critical engineering principle, redundancy. The SIS can trigger different levels of shutdown, all based on the threat. So the most basic is a unit safety shutdown, or USD, which might just turn off our one tank. A step up from that is a process shutdown, or PSD, which could shut down our tank and any other equipment it's connected to. For really big threats, a plant-wide emergency shutdown, or ESD, gets triggered. And in some cases, even after a shutdown, you might need an emergency depressurization, or EDP, to safely vent all that built-up pressure. Okay, let's go back to our diagram and see how this actually gets built out. On the left, that's our original, kind of dangerous system. And on the right, we've added our first real safeguards. You can see a new independent SIS controller, a separate safety shutoff valve to give us a redundant way to cut the gas, and a pressure relief valve right on top of the tank. This is a perfect illustration of our first layer of protection. All right, so now we have a general safety net in place. But, some threats are so common and so dangerous that they need their own specialized systems. Let's talk about fire and gas. A fire and gas system, or FGS, is basically a subsystem of the main SIS, and it's dedicated to one thing, detecting leaks, smoke, or flames. When it finds something, it can do a bunch of things: sound alarms, set off fire suppression systems, and trigger a process shutdown. It's like a highly specialized sentinel, always on the lookout. Looking back at our tank again, you can now see the FGS in action. We've added a gas sensor inside the tank, we've got a flame detector watching the burner, and they're all wired up to their own dedicated fire and gas controller. Now, that controller can trigger a siren and a strobe light to get people's attention and let them know there's a dangerous situation. When it comes to the brain of the FGS, You basically have two main choices. A PLC, that's a programmable logic controller, is super flexible and great for bigger systems. On the other hand, a proprietary controller is simpler, often doesn't need any programming, and is really perfect for smaller setups. The choice really just depends on the scale and complexity of what you're trying to protect. Now, this is one of my favorite parts. How do you actually detect a leak in the first place? Well, this is a differential pressure detector, and it's just a brilliant piece of simple, reliable engineering. The best part? It doesn't rely on complex electronics. It relies on straight-up physics. Here's how it works. This device taps into the gas pipe at two different points. As long as there's no leak, the pressure on both sides of that diaphragm in the middle is equal, so nothing happens. But the moment a leak occurs between those two taps, the downstream pressure drops. That higher upstream pressure then pushes on the diaphragm, which physically moves a contact, closes a circuit, and sends an alarm signal to the SIS controller. It's just so clever and incredibly fail-safe. Okay, so we've secured the pipes, but what about the burner itself? I mean, just dumping gas into the tank and hoping it lights is a recipe for disaster. For that, we need yet another specialized system, a burner management system, or BMS. Let's look at our final system diagram. The BMS adds three absolutely critical components. There's a pilot light, which gives you a constant small flame. There's a flame sensor to confirm that the pilot is actually lit, and there's an ignition generator to safely start that pilot in the first place. The logic here is simple, but it is absolutely critical. If the flame sensor doesn't see a pilot light, the main gas valve stays shut, period. Gas only flows if the system knows for a fact that there's a flame ready to burn it safely. So far, pretty much all of our systems react to a failure that's already happening. But what if we could predict failures before they even occur? This is the big shift from reactive to proactive safety. The key to this is often vibration. I mean, every machine with moving parts vibrates, right? But as components start to wear out, or bearings degrade, or things just come loose, that vibration pattern changes and gets more intense. This is a huge telltale sign of a pending failure. And this is how we track it. We attach these little sensors called accelerometers to critical equipment, like the motor for an emergency exhaust fan. Now, this fan might almost never run, but in an emergency, it has to work perfectly. These sensors constantly monitor the motor's vibration signature during tests, and they feed all that data to a PLC. And the value here is just crystal clear. As the source material puts it, by monitoring the amount of vibration, organizations can make informed decisions about when to repair or replace the machine. This isn't just about preventing a disaster, it's about smart, efficient maintenance. It's about replacing parts based on their actual condition, not just some arbitrary date on a calendar. So, we've built up this incredibly robust, multi-layered defense system around our simple little tank. But as these safety systems get smarter, more software-driven, and more connected to our networks, it brings up a new and really critical question. How do we protect the protectors themselves from threats like cyber attacks? That is a challenge for another day.